Before we complete the next sample exercise, I wanted to point out a process that can be useful in determining a known percent composition or elemental composition. So a sample can be combusted and under oxygen, if we have a hydrocarbon, so carbons and hydrogens, for example, we add oxygen to that and we produce water and carbon dioxide. So this is the same process as we would have seen before when we introduce combustion reactions. So the products will always be H2O and CO2. And we have these absorbers here that after we combust our unknown compounds would produce a certain amount of water vapor and carbon dioxide. And then in certain analyses, we could multiply by a conversion factor for CO2 to carbon, shown here. So we could figure out exactly the mass of carbon in the original sample, utilizing the mass of CO2 produced. The same will be done to determine the mass of hydrogen in the original sample based on the H2O produced. And any remaining amount would be oxygen in this sample. So again, combustion analysis can be useful to determine those mass percentages in an unknown compound. So here in sample exercise 15, we're shown that we have a compound that's composed of 49.5% carbon, 5.15% hydrogen, 28.9% nitrogen, and then 16.5% oxygen. So if you recall, we set these equal to masses out of 100 grams because all of our percentages equal 100%. So that will give us 49.5 grams of carbon, 5.15 grams of hydrogen, 28.9 grams of nitrogen, and 16.5 grams of oxygen. So the next step is the same as previous empirical formula calculations. We're now going to divide by the molar mass for each element found on the periodic table. So we have 12.01 grams per mole for carbon, 1.01 grams per mole for hydrogen, 14.01 grams for nitrogen, and 16 for oxygen. So let's see what these values are in moles for each of these elements. So we have 4.125 for carbon, 5.15 moles for hydrogen, 2.06 for nitrogen, and for oxygen about 1.03. Now, the rule is to divide by the smallest amount of moles. So we're going to divide everything by 1.03, which was our moles of oxygen. So that will give us our ratios, and we'll line these up over here. So 4.125 divided by 1.03 gives me 4 moles of carbon, and that's in a ratio of to 5 moles of hydrogen and 2 moles of nitrogen, and of course 1 mole of oxygen because 1.03 was divided by itself. So now if we arrange these in the empirical formula, we would have C4H5N2O. And this would be the empirical formula for the compound described above. And we're told, we're actually asked one additional item here. So we're going to use this empirical formula to determine the molecular formula. And remember, if we make the empirical mass out of this compound here, we would multiply 4 times carbon, 5 times hydrogen, 2 nitrogens, and 1 oxygen. And we would see that would be about 97 atomic mass units for the empirical mass. And when we divide the molecular formula given, 194.22 grams per mole, we can also use the unit of AMU. We see that that's about a 2-to-1 ratio. So our molecular formula would then be twice the empirical formula, or C8H10 N4O2. So again, based on that molar mass of 194.22 grams per mole, we found our molecular formula to be C8H10N4O2.